Anyway, yes, so I'm going to talk about how to do electronics and especially like how to get stuff up there, like what to do with it. We'll pretty much go over the environment. We'll see what kind of effects it has on the stuff you're designing. We'll see like some ways around to fix some of the issues that you'll be having, and then I'm going to give a little bit of information on like what best practices are for flying in the stratosphere. So here's my background. I work in high altitude platforms for communications. And instead of talking about any of this stuff up here, we're going to talk about more or less public, but maybe obscure information of like how to do stuff and pointers. And also, like if you folks have any questions, like feel free to interrupt. Also, but we'll have some time at the end. All right, so stratosphere is like some stuff above the troposphere, and typically defined 60,000 km to 150,000 km, or sorry, feet. But most of the cool stuff is between 60,000 and 100,000, just because by the time you go above 100,000, like you have to have a lot of lift gas and like your volume to mass ratio gets crazy. Also, when people fly, like they don't usually use altitude, they use pressure altitude. So for our stuff, like if you just kind of think of 5 kPa or kilopascals, that's like roughly 65,000 feet, and it's a good number just to keep in your pocket when you're looking at some of the other graphs. And also, from ideal gas law, at a constant temperature, the pressure equals the density of the gas. So we're going to get a little bit lower in temperature, but roughly if you're at 5 kPa versus 100 kPa, at sea level, you're like, with some hand waving, maybe 7%, 5% of the atmosphere, which will impact stuff like convection, things like that. Temperature is also pretty cold. So this is kind of hard to read, but stratosphere is right in this area here. And this is all in Kelvin, so basically we're sitting at around 200 degrees Kelvin or minus 70 degrees C. And this is, these are mean temperatures, so this is like all year round, which means that actually sometimes it gets quite warmer, so you can get almost to 0 C when you're like being illuminated by the light, or actually get much colder, you can get to minus 100 C, minus 120 C. So you have like this wide range of temperatures available. And then there's radiation. So people fly Geiger counters on balloons all the time. This is measuring gamma radiation, and you can see from sea level up to 100K, it goes up a little bit, but also like UV goes up, other radiation goes up too. So what that means is it'll impact your electronics, but also impact like any plastics you have, because basically something that can last 100 days on the ground might last much less in the sky just because of breakdown due to UV and other atmospheric effects. Also weather. So you see lightning on the ground and you're like, oh, I better get away from that because like I don't want to get shocked. But the truth is lightning goes all the way up to 200,000 feet. And these are called sprites. So this is from EAS, and basically the top level here is around 200,000 feet. So like stratosphere is like somewhere around here. And you can experience 200-300 volts per meter electric field even if you're not inside this sprite, which is a ton. And if you have this big like balloon type object or something else, like you have a cable that's 10 meters, 20 meters long, well, you've just accumulated a lot of electricity. So you have to think about that. And then if that wasn't all fun enough, you also have turbulence. So like a lot of folks here probably flew on a plane. Sometimes the plane shakes. And the plane shakes because you have changes in density in the atmosphere. But also, like if you think about it, as warm air on the ground jets up, it doesn't just all go up. It's going to form these columns, and these columns create like vertices and stuff like that. So not only do you have changes in density, you have motion, and that motion also goes up to the stratosphere. So you can have whatever flying at 50, 100,000 feet. You can experience 5G, 6Gs, like just the thing being shook, just because you're in a stream of air that's moving up quickly and it's varying density. And this is what a navigation chart looks like from ICAO, which is the International Aviation Body, basically advising pilots of like what areas to stay away with. So when they say, hey, we're going to give you a smooth ride, this is kind of what they're looking at, or a digital version of that. So what kind of things can go wrong? So if you go to any Radio Shack or DigiKey and you say, hey, I need something rated to minus 100 degrees C, they'll say, sorry, or they'll just take like the minus 40 C rating and like cross it out, put minus 100, and just hope for the best. So nothing is rated to a lot of the temperature profiles you'll be working with here. So typically you will see general change in performance. Like if you have an op amp, the gain will change. If you have a clock, frequency might change. If you have any kind of tuned circuit, like the performance of that will change. You will have bit flips periodically because you're exposed to more severe radiation, stuff like that. So you should address those, but they're very rare. But in some situations, like if you can create lockup in your device, that can be catastrophic, and you want to make good use of watchdogs, stuff like that, because generally speaking, if it's up there and something is not responding, just power cycle it. And then design it such that you can just keep power cycling stuff until it gives you the thumbs up. And then like some other stuff, like for example, you have EEPROM. So a lot of EEPROMs that you run off normal 3.3 volts or whatever, they have a charge pump. Well, because of the stuff I mentioned before, charge pumps change. So like your write time to EEPROM can change, which means like if you have an SD card, the amount of time you write to an SD card or it takes to write something can change as well. Again, not always, but it's one of those things to keep in mind. And one of the really weird things that I've seen happen is generally when you create semiconductors that are CMOS, so you can create a parasitic bipolar junction transistor inside the CMOS, and it can create a regenerative effect that will eventually toast your stuff. So that's called latch up, and there's different ways you avoid latch up. And I've seen a chip actually fry because it seems like we've undone the mitigations that they put in for latch up. So it's like even that gets weird. Passive components. So a lot of stuff you'll see actually has very fine structures inside that are hidden away. So this is a cross section of capacitor. We have multiple layers, and that's how you get that high capacitance. With dielectric, you also have in resistors, like a lot of times you'll have a thin film resistor where you have serpentine pattern etched on top of the laser. So you have these devices that have these very small structures. They're very susceptible to fracture due to thermal stress because we saw the mean temperatures. So at night it gets super cold, in the day it gets super hot, and stuff expands and contracts. Dielectric changes with temperature. So if you have an electrolytic capacitor, it's going to vary wildly, and like even in some cases, depending what kind of crazy ferrite material you're using for a core, like inductors can change as well. So you have to keep that in mind and either design for it or test. PTC resettable fuses like don't work because basically by the time you get to 0C or minus 20C, like they will operate 4 times the rating. So there's a curve that tells you like what their rating is to temperature, and like they don't even go below minus 40C, but it's like really bad. Even normal fuses don't always operate properly because at the end of the day they are thermoelectric kind of products, and basically if everything is super cold, you can pump more current through and it'll still operate. So, I mean, look at other ways maybe active of monitoring current.
What about just using a different rating fuse, characterizing its behavior down to temperatures?
You could, but then if you're testing on the ground, like you have different, basically like, you have to look at the varying temperature ranges. For some stuff, it's fine. It depends on like what you're trying to do. And then another interesting thing is bond wire. In a lot of semiconductors, you have the chip, and then you have the carrier and the bond wire inside. And that's usually okay. But then if you look at high power LEDs, like the ones that you showed, you usually have a LED chip, and then you have this plastic encapsulation, and then you have these bond wires. So the plastic and the metal underneath have very different thermal properties and expansion properties. So like those things will shear right off. So it sucks, like stuff that you expect just to work on the ground, like your LEDs, not always work when it gets cold, and especially when it gets cold, hot, and cold. And then batteries. So if you want to do stuff in the air, you provide power. So you either have solar panels or you just like put some batteries in, kiss it good luck. And these are a lot of times like lithium ion, things like that, they're not very tolerant to cold. And what usually happens is when you have a battery, you have 2 dissimilar metals where you have electrodes and you have electrolyte in the center. That electrolyte is designed to convey ions. Once that thing freezes, pretty much you can't move anything. So your battery capacity goes down because like you can't move charge. And you can very easily go down 10% capacity and permanently damage your battery if you let it get cold. For LiPos, you want to be above 0C, below 60C typically. Just that way they're more happy. And then the other thing that happens on the far end is, so you have lower atmospheric pressure, which means the boiling point goes down. So if you're overdriving your battery or discharging it quickly, you can lose electrolyte just because it'll evaporate more quickly, whereas on the ground, like, it's totally fine. Oh, and one more thing, also because you don't have convection, essentially because you have your 5% atmosphere, cooling batteries becomes very important too, because if you want to run something powerful, like there's not a lot of ways to get heat out effectively, because just batteries in their nature, even like the flat cells, are kind of resistant to heat transfer. Oscillators. So this is a generic oscillator picture I stole from DigiKey. But pretty much even temperature-controlled oscillators on work well on the ground. In the sky, they start to drift, and they're not designed for that kind of cold. So it's very challenging to get accurate clock. It actually turns out that using GPS as a clock reference and using the 1 pulse per second to train oscillators on your board works really well, because GPS works in the sky just as well as on the ground. And the US government's put a lot of money to give you a very accurate clock source. So it's actually kind of silly, but sometimes it works. Like if your oscillator doesn't work, put a GPS module on. And then interconnects. So like you talked about connectors, it's also a pain in the ass in the atmosphere as well. So like solder is bad because of the thermal mismatch, and then basically like solder cracks. Crimping is great. Run into the same problems, like you can miscrimp stuff, super expensive. But if you're able to use crimped wires, that's great. And also you have to look at your insulator, because like a lot of stuff you buy for ground use is like PVC. PVC is great on the ground. Like it cracks, it comes off in the sky, and especially susceptible to UV. So like Teflon's good, and then there's some other stuff that's pretty good. And then strain relief, because like you're going through turbulence, stuff's shaking. That's probably why some of your wires came loose, because like when you're moving, like things come out. But if you like have stuff stationary, that's all good. But I guarantee you the thing's gonna be vibrating, so you gotta deal with that. And then metal-to-metal contacts. So again, on Earth you have 14 point something psi of pressure pushing down the metal, keeping stuff in. It's actually substantial. So when you lose atmosphere, the metal kind of like pops up because it is under strain, and you have these whiskers make contacts. So this is actually a problem in satellites. You can create cold welding, which is if you have two metals making contact and they don't move, after a while they'll become welded together. So it's super challenging. And then,
You still have whisker problems even with metal solder?
yeah, because metal has granular structure, and there's a lot of stress, and basically as you push those grains out, you can create that kind of interface. And then moving parts are very tough. Like commutators or slip rings are pain in the butt on the ground, huge pain in the butt in the sky. Lubricant evaporates. So like basically you can start out with a good motion, but then like after a little while it'll be terrible. And also lubricants in cold will change their viscosity. So basically something that was lubricant at 0 C can now become something that's gummy at cold. And again, you have the cold welding that we mentioned before. This is a picture of an Iridium satellite, and they have these 4 gimbals that basically connect the satellites together. And their solution to this movement problem is just like not stop moving. So basically, those things rotate as long as the satellite's in orbit. And like once they stop, it's like you have a problem and you have other problems. So they're like, all right, we'll just replace it.
That's like the speed solution.
Yeah, essentially. They watched the movie, like Keanu Reeves came and gave a talk, and they bought into it. And then somebody's asking about EMI, so I do some of that stuff too. Even if you're setting something to like Stratosphere, you want to keep EMI and EMC mindful, or be mindful of it. But the problem is a lot of the standards that are available are designed to protect other people from you. So basically, like, this is DO160, which is avionics EMC standard. This is the mask that you want to keep underneath for dBV per inch. And like this is where your terrestrial radio stations are. So basically they just want you not to interfere with like FM broadcasts on Earth. But if you're in a communication mission, or if you have some kind of sensitive equipment, like a lot of people forget that you will interfere with yourself. Because like if you have a DC-DC converter for like solar panels, stuff like that, typically high efficiency means high radiation because you have faster switching, everything like that. And so you like be very excited about your shiny 96% efficient DC-DC converter that's like driving all your stuff. You'll fly your stuff, and then like you can't get any data off your sensor because it's like, well, you're blasting garbage all over it with your DC-DC converter. So do like a self-radiation scan if this is important to you. But sometimes it's not, because if you just want to set up a GoPro and like look at video, Like, probably won't matter.
Is this appreciably different?
Pardon me?
Is this appreciably different high up in the atmosphere than it is underground?
It is and is not. So high up in the atmosphere, pretty much it's just you there. So on the ground, you'll get interference from other stuff, but you'll still be interfering with yourself. So basically, a lot of people think that, well, hey, I'm like in the sky, so I don't have a lot of interference because everything's on the ground. And they forget about the self-interference. So you'll still have the issue everywhere. But you might not see it on the ground because you might be getting interference from everything else. So, okay, so how do you get this stuff done? Like, how do you solve these problems? Planning is the first step. So, like, define what you want to do, define what your mission is. Like, a lot of people just love sending stuff to Stratosphere, taking pictures. And that's fantastic. If you're doing that, like most of the stuff we saw before doesn't matter. Because you're going to go up, take some photos, like come down, recover your stuff. And also, if anybody here believes that the Earth is flat, like look up pictures from the Stratosphere because you can definitely see that curvature. So you can disprove it and like start Twitter drama or whatever. And then like compare what you're trying to achieve with like what you've built. Like if you want to add a widget and it doesn't solve anything for you, unless it's like getting useful data, just take it off. Like it'll cause problems and like you don't want to deal with that. And then kind of like figure out what's the highest risk. Like if you have a solar panel and it's your only solar panel and you don't have battery packs, then like if that goes out, then you know the rest of it is done. So focus on the important stuff. And again, this seems like super intuitive, but a lot of folks just want to like make the perfect design, like make everything bulletproof. In the end, like it's gonna take too long and cost too much. So just like figure out what's important to you and then try to like really write it out, because you may be surprised, like you'll go through it and it's like, oh shoot, I don't need this VCR in here. Like it look cool, but maybe we don't need it. The other thing is like a lot of folks try to create really fancy PCBs, like you know 201 components, like BGAs, SOCs, all this stuff you see inside of an iPhone. Like if you're doing this kind of stuff, like you're not making an iPhone, make something big. And that means use bigger connectors, use through-hole, like miniaturization will cause problems just because the mechanical stress becomes much more important in those parts. And also like when you do have to debug, if you screw something up, like if you have to debug a PCB from an iPhone, there are a few people that do it, but it's not easy. And then obviously don't use like direct flip chip parts, because those are sexy, exciting, like not for these applications. And then make sure that wherever PCB rolls you use, like the clearances, creepage distance, and stuff like that, they're ready for the pressure that you have, because as pressure goes down, eventually your dielectric breakdown goes up, but then it comes back down again because you have more ions in the atmosphere at that point because you have that UV and things like that. And then plan for thermals, because basically you don't have any convection anymore, so you want to create structures that you can easily spread the heat out in which we'll get into a little bit later. Cable assemblies. Please crimp everything. Like if you need to join two wires, put them in a sleeve, crimp that. Soldering will get you into trouble. You could ask me how I know later.
What kind of trouble?
Just like stuff failing and then you get it back and it's like the solder is cracked. It's like, oh, wasted this perfect good experiment. Be mindful again of the insulation that you use, because basically it'll change the temperature properties of that insulation, and some of the stuff that's good for Earth, 0C minus 20C, will not work well at minus 70C. And for this kind of stuff, like even if you have small vibrations, like stuff will flake off and you have short circuits, then I mean you'll have problems with that. And then this is kind of maybe counterintuitive, but make sure you use the same metal on both sides of the contact when you have mated connectors. So like tin on tin, gold on gold. And the reason for that is because as you have different pressure, you can develop a surface finish there. And even if you have a little bit of moisture trapped, you can develop like high resistance interface. Also, like you found this thing out, we found this out too. You want to have latching and keyed connectors, because again, like you're going to have people help you out. Like you want to make sure they can only plug things in one way. And also sometimes you're going to be like super tired, it's dark, it's cold, your hands are freezing, and like you can't see what you're doing. So even if you're the expert on this stuff, like you will make a mistake. So be mindful of that. And then If you're doing communication stuff, and again, back to EMC, like shielded connectors will save you a lot of trouble down the road because they'll help you keep all the radiation in and like kind of solve some obscure issues. And then thermal management. So again, super cold during night, kind of warm during the day, not a lot of air. So first of all, based on system architecture, decide if your system can go cold, which means like fully shut down, fully get equalized to the atmosphere. For some stuff, if you're taking GoPro up and you're coming back down, not important because you're just taking some footage. Like once the camera dies, it's like, well, we got what we could, and then you get it back. If you do go cold and you have extended mission, basically plan how to bootstrap stuff. And what that means is like identify one power source which will come on even when it's cold. And a lot of times like that'll be a solar panel because batteries, when they get cold, they have very low capacity. Create a very simple circuit. Simple meaning FETs, thermistors, maybe some caps that basically monitors the temperature of the PCB. And all it does is once you're below a certain temperature, just use resistive heaters. If you've added software to this feature, you've screwed up because you cannot rely on any of this stuff before everything gets warm. So just like dumb it down as much as you can. And then create another circuit that basically holds everything reset until your PCB comes up to something warm, where something warm could be like minus 40 degrees C or minus 20 degrees. Because then that way you can kind of, not guarantee, but expect that everything will come up reliably and you don't damage your electronics. Heating. So you're going to have some really hot parts on your PCBs. Like you have DC-DC converters, the inductors will get warm. You might have like some fancy CPUs that generate like a lot of heat running Linux, whatever. Save that heat. So try to use like the ground plane inside your PCB as much as possible to move heat around. Also, they have like graphite tape you can put on the top that kind of spread the heat on top. But basically, since you're already paying for that heat to be generated, like for whatever Linux application, whatever you're using, might as well keep it. If you can't do that, you can get kind of tricky, and then you can try to capture radiated heat from either Earth or the sun. So the Earth actually is quite warm, and when there's no cloud cover, you'll get infrared heat going up. So you could potentially recover that heat and get like 10, 20 degrees C above whatever you were before, just for free, just by exposing part of your electronics to like the radiated emissions from the Earth. Same thing for the sun, but the sun is like very hot, so you want to limit that exposure, or maybe you can get clever. It turns out that actually also for insulation, the Mylar film works great because since we're not conducting heat away through the atmosphere, basically your circuit radiates heat through infrared and other means. And then so if you put a Mylar film, kind of like the stuff you get with balloons at the store, it will both keep heat out from the outside, but also keep heat in on the inside. And you don't have to get like very crazy vapor deposition system. You just get some glue that will stand up to the heat and then just like stick it in. And then as last resort, if you still can't maintain temperature, use resistive heaters for bootstrapping. So resistive heat is basically energy that you waste not doing very much. So see if you can avoid that when possible, and then just like try to capture the stuff from before. Getting cool. So the first way to stay cool is you don't get hot. I know it sounds very intuitive, but there's not a lot of ways you can cool yourself down in the stratosphere. And by don't get hot, I mean be as efficient as you can with the electronics, but also like put Mylar insulation where you can. So if you know like the top of your pail will be exposed to the sun most of the time, and your pail is running kind of hot, maybe insulate the top with Mylar. That way you kind of keep that cool. If you need to stay cool, it's actually very challenging because you can't really put like a fan on there and blow or a heat sink because you're at 5% efficiency of Earth. So on the space station, they have these white panels they pump coolant through, and what they're doing is they're actually radiating heat through infrared. But it's not a super efficient process because you have to have a lot of surface area to make this happen, but you also have to at the same time repel heat from the sun. So if you need cooling, it's going to get very complicated, very expensive, because now you have some kind of heat pipe that might have fluid inside, and then you have to have this like fins that are both lightweight and also have a lot of surface area and good thermal conductivity. And then keep in mind that like running your payload on the ground is going to be different from the sky, and you don't want to overheat in either. Because basically if you can only run it for like 10 minutes while you're doing launch prep, like you're probably going to screw something up because you know, something's gonna be wrong. There's gonna be overcast. You get a phone call, and then like your thing is on fire. It sucks. And then this is very tough to do, but it's good to do testing before you launch, because you wanna. In the ideal case, you'd be able to do hardware in the loop testing and with software and basically run through like an actual flight plan on the hardware that you're going to fly and like actuate all the sensors or mock them and then kind of like make sure you get correct data and your firmware doesn't crash. And this also helps having a defined flight plan. And again, like this depends on what level of involvement you want. Like if you want to have something that flies in the air for a year, then this is important for you. If you want to like have an experiment that just like goes up and comes down. Like if you want to have a pen that went to the stratosphere and you want to write with it later, just like get that artifact, probably not as important. So simulation's kind of cool. And then if you do have an extended flight, having a copy of the hardware on the ground will become invaluable because you're going to see some weird stuff in the sky and then you're like, well, I don't know what's going on. Let me try to reproduce it here. And if you don't have the copy of the hardware, it's going to be very challenging. Yes?
So how long are these missions that you're talking about? What's a long one?
1 year. We also have short missions that last a couple hours because of mistakes that we made. So like a couple hours to 1 year. So let's put that. And then, so the next section, I'm just going to go over a couple of things like about flying, which I thought were kind of cool and might be interesting to you folks. So first of all, like GPS is kind of new in the scope of flying. It works most of the time. Sometimes like the government will degrade it in certain areas just because they're running tests. Like it's super cool, super high resolution, but a lot of people in avionics don't depend on it. And actually, in fact, when you do a flight route, you don't specify GPS locations, you specify waypoints. And these waypoints are called like, let's see, let me find like Arota, so this is in India, Sugid, stuff like that. And they all have latitude, longitude, elevate, or latitude, longitude. And some of them will have like a visual marker on the ground that you can see like, yeah, you're flying over something. And some of them will have a radio beacon that changes frequency as it turns around. So you can kind of lock into the heading of it, and so that way at least you know you're going towards that marker. You might be able to get distance, but then you know when you passed over it. So when you do a flight route, like say from IAD, Dulles to SFO, that flight route will actually have like 6, 7, 8 different waypoints that you hit. And so if you look at flights around the US, you'll see like corridors of flights just because they're hitting the same waypoints, and depending if you're going east, west, north, south, you have different altitudes. So that way they can keep planes like kind of split apart. Also, if anybody here doing GPS stuff or navigation, you know like what sea level is kind of weird. It's kind of ambiguous because we say, oh, the Earth is kind of spheroid. That's why they use altitude. So like, they don't say, hey, I'm at like 100,000 feet. They'll say, hey, I'm at like 2 kPa. So that's how you like communicate. You also have air route traffic control centers. So these are the ones for the US. And inside of here, you have smaller air traffic control centers, or ATCs. So basically, as you're flying along the US or like moving along, you coordinate with ATC, again, depending if you have like a complex thing or not, and say, hey, like I'm in this airspace, like I'm doing this and going here. And they'll be like, all right, that's cool. Or like, hey, no, you can't fly here because we have like a restricted airspace. The universal language is English, and that's globally. So, and the alphabet is NATO. So if you're an English speaker, or like half English speaker, you can contact ATCs all over the world. So you can kind of be a good Samaritan or good citizen, and then just like tell them your flight plan. And usually, if you're in the stratosphere, they don't care because you're twice the height of planes. But they'd like to know because if they see something weird, they know it's like one of you folks and not like a UFO or whatever. And then, so this is FAA, and outside of FAA, you have ICAO, which is a global body, and they have the same thing. They have called FIR, Flight Information Regions. So basically, like you can see a lot of times each country is an FIR. Within each country, you have other ATCs, and then as you go from one FIR to another FIR, you notify them of your flight plan either over the phone or by email. Some FIRs have like really sketchy emails, like on yahoo.com. But you send this stuff there because it's registered with ICAO and like it works. But also like if your balloon is coming down, these are the people that you coordinate with because you're like, hey, So I'm like importing something very quickly. It's a payload.
So is there no standard? You have to call each or email each one of these people ahead of time, ahead of your flight, once you have your flight plan, and
Yeah,
verify with them?
it usually is a one-way thing. We want to be notified like within either hours or days, and they have different requirements based on which region you're entering. And also, some regions are no-fly zones, like based on where you are. Like for us U.S. people, like flying over Russia is going to be a challenge because they'll see your flight plan and be like, no, you can't do that. But a lot of times, basically, you plan ahead, which I'll get to in a little bit, and then just figure out who you're going to hit. And then as you're like moseying along in your vehicle, you figure out like who to contact, which email to send, and say, hey, this is what I'm doing. And then also, if you're getting serious about this stuff and you're staying up for a while, it's good to invest in having a DSB system. And what that is basically it's a way that airplanes know where other airplanes are, because it's a transponder, and basically it broadcasts your altitude and location periodically, but also it accepts interrogation. So a plane can ping you and it will reply. This is a screenshot from Flight Radar 24, which is a website that all they do is they send people these receivers that just tracks planes everywhere. And like, if you have one on whatever you're flying, it makes ATCs feel good because they can see where you are, and also like the plane will see where you are. Because then if you guys get very close, like, you know, lights will go off and they'll avoid you, or like you'll avoid them or whatever. But generally, if you like submit a flight plan, you say, hey, I'm staying very high, I have ADSB, like nobody cares because they can see you, and like if they need to, they'll get a hold of you.
So do you have ADSB transformers on your list?
We do, and you can look them up on HBL or on Flight Radar 24. Yeah, just
Like against the pressure measurement there?
yeah, they convert the feed for you, but you can get those data. If you Google, like, you can find what our designators are, and so you can see all of our stuff. You can see our stuff, and you can see other people's stuff too. But I think it's better to have this available than to be secretive, because like this is a safety system, and also it makes you a kind of a good citizen of airspace, because then you're participating actively in collision avoidance, which is the primary thing you want to do in air safety. And then, like, if you're going to be up for a while, it's good to plan for telemetry. So this is EchoOne. Literally, it's the first communication satellite that Earth launched, or NASA launched, I guess. Literally a balloon. So I guess it's fitting for the talk, but basically it's a balloon that like expands in the stratosphere, or sorry, like 1,000 km, something above, and all they do is they bounce signals off of it. And it is a satellite because it's in orbit. And like it is for communication because it like reflects stuff to you, but it's like fully passive. And in the 60s, this was hot stuff. Like people really loved it, and it's great. When you do your telemetry, something in ISM band like 900 megahertz, 430 megahertz, like getting one of those radios should be okay. Getting a 100-kilometer link off that radio is doable with like reasonable antennas. Challenges, you have to have ground infrastructure. So as your balloon is flying along, like you get in the car and you have to keep following it periodically. And that's like, some people like it, some people don't like it at all. Because if you're an office person, probably not going to work out well. Another option is you can use satellite coverage.
Are there no reference ground stations that
There's maybe some ham stuff. I don't know of any that will just like let you track, but there might be. And you might be able to like coordinate with people too and say, hey, can I put something in your backyard?
There are APRS repeaters that SAM stuff, so you could easily use those
Yeah.
if you're an amateur, but if you're a company, it's probably be a bad citizen.
Yeah, but I mean, look around, because there are some stuff available, and there's other infrastructure that you can tap into, like even if you have like VHF and stuff, because that travels quite a bit, and if you have power, you can just drop an antenna down. Another option is you can work with like Iridium and Inmarsat satellite providers, and there you get about $100 a meg, like reasonably priced for that kind of data. Kind of expensive, but the upside is basically they have all the network already set up. You just fly your stuff and you can sit in your office and like the data will come in.
The point of your balloon is to provide internet access, right?
Yeah.
So how do you're not paying $100 per megabyte for the internet that you provide to other people?
No, we have two types of service, right? We have communication service provided to people, which is in the service region. Then we also have, it means that we can always reach a balloon no matter where it is. Because so this is more for command and control, because Again, ATCs are nervous. If you say, hey, I just sent something flying overhead, like, we don't know what will happen, but we'll let you know. Versus you're saying, hey, like, we have eyes on it, we know where it is, like, we know what it's doing. And you could augment the two, right? So you can have one that's like running your ISM band down to Earth, but you can also have like a satellite system that's just there just in case. And depending on who you are, if you're like academia, you might be able to get away with, like these companies are generous in certain cases. So you might be able to approach them and say, hey, like we're a bunch of students, like we want to do some cool stuff, can we get some data? And they're like, yeah, this looks good for PR, let's do it. And then also like for planning stuff. So if you're working with a balloon, like balloons don't really have a lot of mobility. They can, depending on how you change the density of it, they can move up and down, but they don't have a propeller. You can't just say, hey, like fly over there. So basically you're at the mercy of the winds. And I'm gonna give a shout out to the European Center for Mid-Range Weather Forecasting because they do a much better job than NOAA providing wind charts. So they have this stuff available. It's like an FTP service. You just go and download like today's data. So they give you today's wind layers and the predictions for like tomorrow and a couple of days out. So you can like pick your favorite numerical package and just do some simulations and figure out, hey, like if I float up this way and I stay here, like this is likely the area that I'll be in within whatever days, and then that's how you generate your flight plans that you submit to like ATC and stuff. And they also have like a super cool simulator where it's like a JavaScript Earth that you can zoom to different layers, and it's just very interesting because you see all that stuff moving. And then it's good to fly or plan flight termination, because like sometimes things will happen. Like let's say like all your electronics is toast and like you can't do anything with your balloon anymore. Like no, it doesn't make sense to just let it fly and keep monitoring it because your time is important. Or let's say you screwed something up and you're about to enter like Nellis Air Force Base airspace. Like the federal government has no humor about flying objects landing on their military installations. So if you do that, like you may be able to get an escort to pick it up, or it's going to be like confiscated forever. If you land on SFO or LAX, you're going to jail. Like that's it's a fact. So you want to have a plan to terminate your flight, like to cut it down somehow when you need to. And like a lot of people when they're designing it, they think, hey, I want to make this stay up as long as possible, but at the same time you need to have like a way to just shut down the experiment. Because maybe you see aliens, maybe you're learning too much, whatever. Like think of this in mind. So that's about it for the presentation. We talked about the stratosphere and like the environment you see there. We covered some of the effects on materials and electronics. We talked about some of the stuff that hopefully you can use to mitigate some of those negative effects. And then we saw some stuff that I like about flight, maybe like was useful for folks here as well. So with this, here's my contact if you want to hit me up. Questions? Yes?
So you showed that chart, and that was by altitude, the different currents?
Yeah, it's hard to see from here, but what they'll do is they'll give you a stack. So their website has a visualization, but what they do is they give you wind layers and like the directions, the vectors for different wind layers.
So then you can adjust the altitude of the
Yeah, that's one of the stuff that's not general knowledge. So if you look online, you can figure it out, but you didn't hear it from me. Yes?
So you said you're running Linux. Like, were you able to get some standard industrial components for your balloon? Like, can you take a Raspberry Pi and fly it in the stratosphere, or did you have to design everything on the balloon to work in those conditions?
Hey, so we work for a very rich company, but we're like super cheap bastards. So for us, custom design besides PCB is a no-go. Like, we don't do custom silicon. Like, we'll take some off-the-shelf parts and we'll like package them in a way that makes sense, and we'll keep them warm, keep them happy. But yeah, like flying Raspberry Pi, we're not flying Raspberry Pi, but it's within the same scope of stuff. But yeah, like industrial temperature range is our favorite, just because like otherwise it gets super expensive.
So you mentioned running cold, so letting your components cool down below -40. The behavior of the components is specified down to -40. Do they ever attempt to characterize what happens to them when you get cold with that? And have you run into any problems?
So the answers we get is like either no, or like a no expletive, or just like they don't reply. Basically, characterizing -40 will require one of two things: either for you to do it, or to pay somebody a lot of money to do it. But basically, you have to validate this stuff and you have to accept a certain amount of failure. But nobody will do that. Some companies will sell you parts that run colder. There's some exceptions. You get like minus 60. There's some companies that will sell you integrated circuits that go to minus 80. And what they've done there is they've basically done like a sample size, and then they've characterized those parts that they sold to you. And the markup usually is like 10 to 50x.
So is it like almost like running Spaceball parts, but for a Stratosphere application?
Yeah, but even like the satellite people don't do that. Like the satellite companies will keep their stuff at like 45C all the time. Like if yeah.
Like heaters to keep it that warm?
Yeah, they typically a satellite will never go cold, and if it goes cold, like it'll have other problems, and that might be the end of mission.
How do you guys weigh, for such long mission duration, redundancy versus part quality?
Well, that's a very good question. We try to hit a certain metric for performance, and we try to validate our design to meet that metric. And basically, we try to do the least amount of effort to get to, let's say, 95% reliability over a certain amount of time. But then also, we make our system fault tolerant, like especially for soft faults. Because basically, if you have firmware is hard. Like firmware will crash. If you can recover from a firmware crash quickly and get back on your way, then to me, that's much better than having a system that will always stay up. So we'll design for that, for example. So we'll try to have something that's, nimble, I guess. I don't know. Yes.
You mentioned fields of a couple hundred volts per meter, and those are static fields. Do you ever get interference from dynamic fields in the atmosphere?
So those are not super static because it's pretty much the same time scale as like lightning. So it'll be 200 volts per meter for like a couple of milliseconds. We don't really get a lot of interference from like cyclical or repeated kind of noise, but basically we'll have effects like lightning, stuff like that. We'll have some other discharge, and then also you have a concept of antenna temperature. So depending if your communication system is facing towards the sun versus away from the sun, you can get different background noise levels, and that's kind of like a Brownian motion. Anybody else? And then if you guys think of questions, you can let me know later. But yeah, go fly some balloons.